Welcome to AP Calculus AB Section 2.05. I'm Luke Williams, and today we are going over continuity. As you can see on the left of your screen, we have a graph with several discontinuities. Can you explain where all the discontinuities occur and what these discontinuities are called? If not, that's totally okay. That's part of what we're here to correct. If so, you're already ahead of the game. So a quick refresher about the definition of continuity. A function is continuous if, at number a, the limit of f of x as x approaches a equals f of a. For this to happen, the limit as x approaches a from the left must equal the limit as x approaches a from the right. In addition, f of a must exist. When these two things are true, then check if the definition statement, or the limit as x approaches a of f of x equals f of a. If all these things are true, then a is continuous. If not, then there's a discontinuity at this point. For example, in the graph shown on your screen, as x approaches 1 from the left and from the right, do they equal each other? Do they equal f of 1? And does f of 1 exist? Since the answer to all of these questions is yes, the function is continuous at this point. Here's a quick example of finding discontinuities. If you want more time on this problem or any problems in the future, please feel free to pause the video before I go over the answer. Same thing with my work. Sometimes I'm moving through this pretty quickly, but you can always pause the video. The first step is to factor out the top. It can quickly be noted that there is an x plus 2 on the top and on the bottom. These create a hole at x equals negative 2, so the function is discontinuous there. Some students might cancel out the top and the bottom and assume there are no discontinuities. It's important to be careful before making moves like that, because you could be getting rid of an answer, which you would be doing in this case. So as you can see, the only difference between this question and the question above it is that 0 when x equals 2. And what that 0 does is it actually makes this function continuous, because the limit as x approaches 2 from the left now equals the limit of x approaches 2 from the right, and f of 2, which is 0. So this function is now continuous the entire time. Type of discontinuity. There are 4 main types of discontinuities that we are going to be going over. The first one is removable. This occurs when you have numbers in the numerator and denominator. Because these can be cancelled out to find limits, they are called removable. They can be filled in with just one step or one move. The next type is a non-removable jump discontinuity. A jump discontinuity occurs when there is a so-called break on the curve. For example, in that function in the bottom left of your screen, the limit as x approaches x from the left, let's say that's 1, and let's say that second one is 2. So the limits do not equal each other, so the function is not continuous. At that point, it's a jump discontinuity. A non-removable infinite discontinuity is also known as an essential discontinuity, and it occurs when the curve has a vertical asymptote. So let's take that first blue function. There's 2 vertical asymptotes, one going towards negative infinity from the left side and one going towards positive infinity from the right side, which means that there are non-removable infinite discontinuities or essential discontinuities. The two are interchangeable. The final type of discontinuity is a point discontinuity, and it just means that there is a point above a hole, so the limit as x approaches a is not equal to f of a. So now let's try using our new vocabulary to label these discontinuities. So what is going on at x equals negative 2? X equals negative 2, there is a point discontinuity, because there is just a point above the hole. At x equals negative 1, there is a non-removable jump discontinuity, because the limit as x approaches from the left and from the right do not equal each other. And at x equals 1, there is an essential discontinuity, or the vertical, the non-removable infinite discontinuity, because there are vertical asymptotes. Functions that are always continuous in their domain. This is more important for things in chapter 4, but it also comes up in IVT, so it's important to know this, even though it's not used specifically in this section. It is continuity stuff. So polynomials are always continuous: logarithmic, rational root, trigonometric, inverse, and exponential functions. Rational functions are interesting because they are always continuous in their domains, but that doesn't mean they are always continuous. For example, a hole. So you have, it's because a hole isn't considered in its domain, that means that it's continuous, just not the entire time. What you'll most likely be tested on. Definition of continuity is something that comes up quite a bit. Given a function, determine points of discontinuity and be able to label them, or given a graph, determine points of discontinuity and be able to label them, and explain your reasoning using the definition of continuity. Graph a given function that may have one or several points of discontinuity, and these are the really important ones. Find c so that f of x is continuous, or even harder, find a and b such that f of x is continuous for all of r. And we will be going over those two in a second. So first, sample problem number 1. Given f of x, find all values where f of x is discontinuous. What type of discontinuities are they? So the first step in this problem would be to factor out the top and the bottom. And when you do that, you get this, hopefully. So now that you've done that, you see that there is an x plus 3 on the top and an x plus 3 on the bottom. That means that there is a discontinuity x equals negative 3. It is a removable discontinuity since the 2 would cancel out. Now, find c so that the function is continuous over all of r. The first step is your calculus step. It's to set these two equal to each other, because the limit of f of x as x approaches 2 should equal f of 2. So these two must equal each other. From there, it's really basic algebra. You literally just plug in 2 for x, and now you find c. And c equals 1, which means that in order for the function to be continuous over all of r, c must be equal to 1. And to check your work, it's pretty simple as well. You plug in 2 for x and 1 for c, and since the 2 would be equal to each other, 3 equals 3, you know that you've done your work correctly. This is the hardest problem that they can give you about continuity, and it isn't terrible. It looks worse than it is. So let's dive in. The first step is the calculus step, and so you have to find the first equation must equal the second equation at x equals 3, and the second equation must equal the third equation at x equals 4. So you use calculus and limits to justify plugging numbers in, and you get the two equations, 9b minus 3a equals 2, and 17b minus 5a equals 8. Now that you've done that, you just use algebra to find b, and you find a. And that can be a little bit tricky. You have to be very careful with your work, but once you do it, now you can check your work, and you plug the numbers back in, and you make sure that you've done it all correctly. And you found that a was about 6.2 and b is about 2.29. Since I made this problem up, the numbers aren't too pretty, but the limit as x approaches 3 from the left is about 6, and from the right it's about 6.01. So you know that x approaches 3, the limit is about correct. You've solved that correctly. And for x equals 4, about 15.84 and 15.91. So again, you know you did your work correctly. Thanks for watching, everybody. I hope that you got something out of this and you know your continuity just a little bit better.